For the next aspect of this session, we'll have a discussion, and there will be 4 questions that 5 experts on the panel will address one at a time. So each question will have 15 minutes to talk about, and each participant can talk for about 4 minutes. So which isn't too long. So the first question is, what characteristics of light are related to circadian disruption? How well do satellite images measure light that causes circadian disruption? Dr. Blask?
Well, I think it's clear, not just from this session, but from research that has gone on for many, many years, that the characteristics of light that are important for so-called circadian disruption are intensity, wavelength, duration, timing, and then maybe some other new terms that I'm not familiar with yet. But those are the basic terms. And I think that a lot of it depends on what aspect of, again, circadian disruption you look at. Obviously, you look at phase shifting. You can look at amplitude changes, particularly in melatonin. And I think the phase shifting responses with respect to intensity and certainly wavelength, and the amplitude changes, particularly in melatonin, there's a lot of congruence there. I think there's agreement there. So I think those are the characteristics of light that can invoke circadian disruption, or at least encourage it in a way. The question about how well do satellite images measure light that causes circadian disruption, I don't really have a good opinion about that. I mean, what Mariana just presented would suggest that perhaps it doesn't. And Mariana didn't really talk about the endpoint of those satellite studies, which was prevalence of breast cancer, and in the more global study in Israel, and then the more global study, prostate cancer, as I recall. And so it appeared that in areas that were where there was more illumination, as detected by these satellites, that there was more prevalence of breast and prostate cancer, and conversely, where areas were more dimly lit, there was a decreased measurement of prevalence. So whether those intensities of light that were measured by those satellite images were enough to cause circadian disruption that was responsible for those changes in prevalence, I guess those of us who favor the effects of melatonin being an anti-cancer agent, and that bright enough light can suppress melatonin, might buy the idea that there may be some cause and effect there. Others may not. But I think it's an arguable point. What do those satellite images actually represent? I know in those studies, maybe Richard will talk about this a little bit more, the confounding factors were presumably taken into account. So I don't have a good answer. I don't have a good feel for that. So.
Okay, thank you very much. Dr. Gorman?
So I also have to, well, I wouldn't say, I will plead ignorance on the satellite image question, but with respect to the other questions, I think I agree with everything that Dr. Blask has said. But I would add, I think, one important thing, which is light history, or and the sort of prior status of the circadian system. So we've known for a long time, for instance, that the entrainment state markedly affects how animals respond to light. So in a long day condition, in a summer condition, our circadian system has a relatively narrow interval, maybe a third of our day, or a third of our 24-hour fraction is light sensitive in terms of the ability to shift the circadian system. And the response of the circadian system in terms of phase shifting is much attenuated. We've extended that work actually to light sensitivity, which is not the same thing as the size of the shift. And we've shown that in rodents, manipulating photoperiod changes the light sensitivity 40-fold, so like 1.5 log units in terms of not in terms of melatonin suppression, interestingly, which was separate from that, but in terms of the ability to cause phase shifts and to induce PER1 expression in the SCN. So that, I think, is something that is potentially pretty interesting. I think one of the things that we kind of need to think about is, and one distinction I think we want to really talk about is the difference between light at night and light in subjective night. So this idea that we make this shift from a daytime physiology to a nighttime physiology, and I think very few people would be willing to sort of fraction that physiology on a 12-hour basis in modern society. So, as Randy said, we are in a long day state. Potentially, and so we might want to make the distinction between light during the solar night, but during our subjective day, versus light during our subjective night, which is also happening at night. And in many of us, people who are phase delayed might be happening in the morning, where the solar day has already begun. So I think I'll leave it at that for now, and maybe come back.
Thank you for your comments. Dr. Figueroa?
Yes, I guess it's just following up on the presentation on the comments. I agree completely in terms of the lighting characteristics. It's not one lighting characteristic, it's the interaction of all these different characteristics. And I think the photic history, it has to do for us, I believe, that the buildings are too dark during the day. And that may be actually increasing our sensitivity to evening light. So I think that, of course, we all care about energy efficiency and energy codes. I work a lot with that more on the architectural lighting part. But I think we have to start thinking about as a whole package, not just light at night per se, but really the total light exposure. I think in terms of the satellite, and to follow up on Dr. Blast's comments, there's no question that the studies did show a relationship. And it is my point. I think that what happens is in places where you have more electric lighting, you have more social activities. People in New York City are out a lot later than people in the Midwest because they have more things to do. They have more social things to do. Now with social media, kids are in front of computers and iPads and communicating with each other. So I think it is sort of to me, it's more of an indirect relationship. Even if you don't get enough light from street lights in your bedroom that will directly suppress your melatonin, the fact that you live in a place where you have many restaurants and many social activities, that's disrupting people's lives. And, we're not really following the natural. I mean, if the lights go off in the evening, you don't have lights, what else do? You go to bed, you sleep, right? You don't have anything else to do, that's what you do. So I think that looking at light as an enabler more than a direct, that was the point of bringing it up. I think physically, the data suggests that, with satellite images directly, you're measuring things that are less effective for the circadian system, but that does not mean it doesn't have an indirect effect, which is what I think the epidemiological data are showing.
Yes.
Very good. That's what I was going to say in response to your talk. That was the rationale for these original studies. We didn't have any. We weren't claiming that the light from the outdoors was coming into the bedroom per se, but as a surrogate for the opportunity for much more of a lighted, light being out and what have you. And for those who are interested in getting into the weeds on this, we did have a nice exchange of papers, Chronobiology International in 2011. I responded to their paper in, I hope, a thoughtful way. And we also see the ecological studies. The reason we wanted to do them at all was as sort of a necessary but clearly not sufficient thing for there being a large effect. A lot of people say, well, if there's any impact of light at night on breast cancer, it has to be very tiny, if at all. And I disagree with that. And in particular, the ecological studies were to say, if there's a large effect, we should see this relationship. It's not enough. There's potential for confounding and that. And finally, we've already brought this up, and I'm getting redundant and boring myself. The potential for direct light at night, suppression of melatonin, and then the indirect or enabler aspect of electric lighting on, for example, meal timing.
Thank you, Dr. Stevens. Dr. Nelson?
Now I have nothing to say. Well, I would like to agree with Mariana about the importance of having bright lights, bright bluish lights during the day, and I think our vulnerable patient populations, those in nursing homes, live in basically caves. They're in dim light all night and they're in dim light all day. They rarely go outside. In our hospital patients, the same situation, and so I think that's in our kids too. Frankly, are in that situation, and so focusing on making sure the circadian system is entrained, as Michael said, is going to be important. And you need the short wavelength lights early in the day, and then you need those to fade off into the more sunsetty colors at night. So I think we know what the characteristics of light are. Basically, it's the brightness, it's the wavelength, and it's the timing. And so I think we just need to pay more attention to that issue. I know nothing about satellite imagery, so let me talk about that. It's a very strong correlation in the 2 or 3 or 4 papers. 4 papers have been published on that topic, and so that's great. What I think we have to encourage, and the NIEHS is in a position to encourage that more than me, is, what about the studies that didn't show the correlations? Do those studies exist, and can we publish those null data so we can see, we'll start to zero in, is this a possible cause of effect, or is this a correlation that happened in a few studies? So, if there's only 4 or 5 that worked out of 100, then you start to be suspicious of those data. But my sense is those are the ones that were conducted, and those are the ones that all worked. And so I'm confident that it's showing us something, and then we need to get in there with more mechanistic studies to see what exactly it was that caused these relationships.
Yes, you can go ahead.
I do want to bring it up, maybe perhaps for discussion later in the afternoon. I think maybe we should start thinking about not just electric light at night, but just social jet lag. I mean, I think we're not talking only about light, which is, I think it's an enabler, but I think there are other enablers, and I think we have to expand that because things are changing. Kids are in front of computers and social media and talking to other people in other parts of the world and sleep depriving themselves. So I think, are we talking about a social jet lag, which Till Ronenberg showed it exists, which light at night is a part of it? Should we expand that definition or not?
Thank you. So the next question is, how can experimental evidence, animal studies, and/or biomarker studies in humans inform the interpretation of studies of health effects in humans? And also, how do we translate animal studies to human studies when it comes to sensitivity to light? Dr. Blask?
Well, the first question is a mouthful. It's a lot to digest. And I'm still digesting my breakfast, so I don't know if I have room for this, but you have in parentheses here animal models of outcomes and biomarkers and or in vitro studies. Let me go with, I have a personal bias with regard to working on circadian system and especially light at night effects, using to try to get it questions of in vitro systems. I worked in vitro models of cancer for many years, and I fell into that because we wanted to work on mechanisms. You know, everybody, NIH is obsessed with mechanisms. So the only way you can really look at mechanisms, you can't look at mechanisms in vivo, so you got to go in the dish. And we got stuck in the dish for many years, and we finally got back out of the dish, and I'll never go back to the dish. So I personally don't think, I think we can learn some valuable things from in vitro work. Don't get me wrong. That's really given us a lot of excellent information. But until we use in vitro systems that we can at least approach mimicking in some way a circadian type of model. For example, we're toying with a system now where we try to expose through a flow-through system cancer cells to a circadian type melatonin signal and try to recapitulate what happens in humans. Of course, it lacks all the other circadian aspects as well, but it may be better than putting melatonin in a dish in a static in vitro culture and letting it sit there for several days. So until we do some more imaginative things like that, I think in vitro studies are going to be somewhat limiting, especially when we're talking about an environment. If we're talking about a target organ like breast cancer cells or even normal cells, if you're culturing retinal ganglion cells and exposing to light, that would be very, very useful. I can't speak to that. I think animal models are very, very important and I kind of alluded to this, was it yesterday? Yeah, it was yesterday. Yeah, it does. And the idea came up about, well, we don't really know what a baseline is in humans because we're awash in light at night, and we have, as Michael Gorman pointed out, we're in this kind of subjective night and subjective day, and so it's kind of very fuzzy. Whereas in animal studies, we have pretty well-defined light-dark cycles that we use, and the traditional one is 12 hours of bright light and then 12 hours of darkness. Although I will say, and this is a problem, this is a very big problem, most animal facilities have their animals in a dark room. The lights go off, but there are light leaks under the door and through the door jambs and even windows where hallway light is coming in. And if that's the case, you don't have your animals on a photo period, as far as I'm concerned. And this is a problem that we had to contend with going to Tulane University. And all our animal rooms are absolutely light tight, and they're constantly monitored for that. We had light contamination in a previous institution that affected our cancer experiments because dim light was leaking into the room, and we saw 2 times faster growth rates in our tumor models, and we couldn't figure it out, and we suspected maybe it's the light, and we couldn't believe it could be that little light that might do it. But as Mariana indicated, animals are much more sensitive to light, generally up to about maybe 1,000 times more than humans. So we did the actual experiment where we subjected animals to the same dimness of light that was coming through the light leak doors, and in fact, that's how we fell into dim light at night as a way to manipulate just the melatonin rhythm without affecting kind of the general circadian activity as a model system. So the animal models in the properly lit rooms are critical, and that has to be absolutely solid, in my opinion. And I think we can learn a lot from the animal models. And I think we have to start, again, being more imaginative and perhaps modifying our photoperiods, making our photoperiods more, create a transition to a dark environment like we do in, supposedly, if we live in a natural environment. Of course, we live in an unnatural environment, so the transitions are not there for us, essentially, as well. But I think we need to start thinking about trying to mimic what we see in real society in some of our animal model systems. But I think they could be very, very useful.
Thank you very much, Dr. Gorman.
Dave, Blask.
What? Blast, I'm sorry.
Sorry.
I believe we're at Dr. Dr. Gorman.
So I'll say it for the third time. Yes, the mice are not humans. Mariana said it, and Dave said it, and I'll say it. And in terms of in terms of what intensities are equivalent, and just to sort of highlight this. So Randy's beautiful studies with dim light at night, 5 lux. It seems dim, but how where does that sort of fall in terms of the human equivalence? I'm not sure about that. And so I think it's a great term. I think it's an outstanding model. We also have a model of dim light at night, but the dim light at night that we're using is less than 0.1 lux. And we contrast that with complete darkness at night, 0 lux. And what we see is that the circadian system is profoundly different under these conditions, and in a great way. And so to Dave's point, it might be that darkness is deeply unecological, because certainly nocturnal rodents are exposed to starlight and moonlight, and they have a little bit of light at night. And one of the things that we've found with dim light at night is that it doesn't induce phase shifts, it doesn't suppress melatonin in hamsters, but it makes the circadian system profoundly different. It makes it much more adaptable to changes in photoperiod, to changes in non-24-hour cycles. We can induce novel waveform entrainment states. We can do all sorts of things. And so I think we've underestimated what a rodent circadian system can do by using this very, very experimentally clean, complete darkness, but ecologically irrelevant stimulus, which is complete darkness at night. And so, I mean, it's whenever I write anything, because of Randy's great papers and influence, I always have to make add a statement about, well, we're calling it dim light at night. It's very different from somebody else's dim light at night, and it's orders of magnitude less. It's a different thing, and so. The beautiful fluence response curves that Mariana showed us with melatonin suppression, I think, are very similar for phase shifting, but we know that there are these other effects of light that are not going to fall on this. They're not going to look the same as those fluence response curves, and we still have a lot to learn about that. And when we think about it in terms of vision, which is going to be, light is going to enable vision and change our behavior. That's going to have a very different phase fluence response curve from melatonin suppression, phase shifting, from other effects on the circadian system, alertness. And so sort of teasing these out and seeing their different dependencies is going to be a key issue.
Thank you. Dr. Figueroa?
Yeah, I actually agree, and I have to say I love your set of studies. I saw your student presenting. To me, what I find it really beautiful is you do convergence. You attack in all these different ways, and you get the same results, and everything fits. I mean, I think it's just absolutely beautiful. And I agree with Michael. I think the thing is put into perspective what 5 lux for an animal is, which is probably 5,000 lux for us, which is daytime light levels, which we're probably not going to be exposed to in the middle of the night. But yet, I think it's important to start doing the animal study. Animal models are extremely important for this kind of work. I mean, we're working now with getting data from the Nurses' Health Study that we collected in the field, translating that into comparable light levels for animals, and we're starting to look at different shift works with insulin sensitivity, and we're clearly seeing that when you equate the light, you disrupt them, you're seeing an effect in insulin sensitivity and glucose production. So it can be done, it can be translated. I think it's just a matter of us agreeing, everybody making sure that you're doing the sums right and you're translating. And I completely agree that we need to start thinking about not just one aspect of the lighting, as we talked about. You have to look at how all these different effects of light, the photoperiod, the background light, the photic history, how these things affect. And I think animal models are pretty much perfect for these kinds of studies. So.
Okay, thank you. Dr. Nelson?
There are other animals besides mice. And I think that they're informative too. And so I think that the NIH narrowing of what an animal model is, musculus, has not been a great way to go. And I think looking at diurnal creatures, diurnal rodents who have a spectral sensitivity and an intensity sensitivity that's much more like ours, can inform us in a good way. The ones we use are vicious. They bite, right? I have somebody who's worked with them. They're not as easy to work with mice, no question about it, but the information, I think, is valuable. I know I wouldn't be wasting my time. The animal models are valuable in this sense, and they can be translated. Michael's work is on less than 1 lux, which is like 0.01 microwatts or something like that. I forget. It's very low-level microwatts per cubic, right? I mean, and so, you know, when we give 40 lux of white light to humans and look at fibroblasts, we can see a suppression of the amplitude of some of the clock genes. So I think somewhere between 40 and 100 lux seems to affect humans. Now, in terms of the melatonin, again, I don't think that's I know it's easy to measure and so on, but I don't think that's the core issue. I think it's the disruption of the clock mechanisms itself, and as Fred said several times, and then the dysregulation of the peripheral clocks that may be driving the other things like sleep and melatonin that we measure secondarily. But that's my conceptualization of it. I don't know that people share that necessarily, but my conceptualization is based on the data. So I think it's very useful to use the animal models. I think you do have to understand, as reviewer 2 has taught me, that mice are not people. But you can get around that by looking at different kinds of animal models. And, you know, we may need to bring back non-human primates.
Thank you. Dr. Stevens?
Yeah, for me, for breast cancer, melatonin suppression per se is front and center. The circadian disruption, the clock genes, were terribly interested in that as well. Those of us trying to do these studies, but as I mentioned up there, the toxicology of melatonin is just so strong. It can just prevent DMBA-induced mammary tumors in Sprague-Dawley rats, whether there's. And then to the animal models, an analogy that I like to use is from observational epidemiology, we have proven that smoking causes lung cancer. The term cause meaning causally increases risk 10 or 20-fold. How exactly it does it, I don't know that there's consensus yet, and it doesn't matter. We just hope to reduce smoking in people. Whereas, coming specifically to the shift work aspect of this conference, which is important, shift work is going to be done. And so if shift workers are truly at increased risk of breast cancer, and these other chronic diseases, we need to understand the mechanisms for how that works. And so the animal models, I think, are, from a practical point of view, very valuable in that regard.
Thank you. So we move on to the next question. Which animal exposure models are most representative of potential human exposures and should be considered by NTP? Conversely, which animal exposure model should be excluded? Dr. Blask?
I'd like to make 2 basic points about this, but let me preface those 2 points by just saying I don't think any animal model should necessarily be excluded if it can address important questions about the circadian system. So, having said that, though, I have a personal kind of conflict in the sense when I think about circadian studies, particularly in cancer, but it holds for metabolism and probably any disease state you're going to study, is that a lot of the studies in cancer are done in mice and in mouse strains that don't make melatonin. So we've learned and can learn very important things about how the circadian system regulates cancer. There's no doubt about it without having the melatonin signal there. And we draw a lot of the information that we use for our own studies from that database. However, at some point, if we're trying to model for humans, ultimately, humans have a melatonin signal, okay? And the melatonin signal has its own universe of things that it does as a chronobiotic, anti-cancer signal, or metabolic modulator, whatever you have. Pick the target organ of your choice. It does talk back to the suprachiasmatic nucleus, and it helps to reset the clock. Maybe it's not as strong as light per se, as I understand it. So in the mouse models that don't have a melatonin signal, you're missing that, okay? So I think we have to start acknowledging that a little bit more and synthesizing those two. And that's one of the reasons we are very adamant about using a rat model that reproduces a very, very human-like melatonin signal in our work, because we think it's very important, not just because we're working on melatonin. Even if we weren't working on melatonin per se, I would feel that it would be important to have that component there, because the cancer mouse strains that are used are essentially melatonin knockout mice, in a sense. The second point, and I'll end with this, is I think we have to start to come up with more imaginative models that may combine human and animal work. Bud Brainerd, his group and our group, tried to start doing this in early parts of 2000s, and we came up with a model system, and it's particular for melatonin, because we can capture a certain melatonin level at a particular time of day. So it makes it more amenable for that, where we can draw blood from humans at different circadian times and take that blood and perfuse it directly through human cancers. The blood never goes through the animal that's housing the tumor. So it's human to human. And I think we've learned some very valuable things about melatonin and light at night suppression of melatonin in cancer. And I think there may be opportunities to try to look at other kinds of relationships like that by combining human clinical technology with animal technology. Not for everything. Every model has its limits. Our models have their limits. We know that. Nothing's perfect. But I think we need to start being a little bit more, I hate to use the term out of the box. I'm getting tired of that. But you know what I'm saying.
So can I just also clarify, because maybe I just clarify what one of the things that we wanted in this question too, besides that, was I know there was some questions on some of the initial phone conversations about sort of the genetic models, and should we be including the knockout mice in this for the clock genes and the surgical models in our evaluation, or should we just be concentrating on the models of exposure? And so I'd just like to hear everybody's comments on that too. That's all.
Okay.
Well, since the microphone's right next to my mouth, I'll come. Well, it depends on what you want to look for. If you're talking about light at night, okay, and it's what Fred alluded to, external disorganization. in the environment, well, then maybe a genetic, if you're strictly going to limit to them, maybe a genetic model may not be the best, but I don't know if you could really totally eliminate, because you may eliminate some gene that has an important function of running some organ that you can learn something very valuable about in terms of a light exposure in missing that gene.
So the genetic models would be informative in terms of mechanisms.
Yeah, I mean, I think
But,
that's,
so when we do our evaluations,
Yeah.
we make a conclusion about, just the way we do stuff with RC is about the evidence from animals, is it sufficient? And so maybe the genetic models are important for the mechanism, but not quite so important for the determining sufficiency for light at night. That's the
I
way
don't-
I think I'm reading it.
I don't know. I mean, you do research and things change. You learn new things, and then things you thought about before, you go, we were full of crap back then. We shouldn't have thought about it that way. So I think we got to be very open-minded.
I think, okay.
Just one comment. Ruth, I was wondering if you can expand. You mentioned sort of about how you consider the animal, but you also have the option that mechanistic data can sort of alter your conclusion. So maybe if you can expand on how you consider.
So just in terms of our criteria and when we do our evaluations, it's sort of similar to IARC evaluation. So we have the human evidence, we make conclusions about the level of evidence, we make calls on the level of evidence from animal studies, and then we have mechanistic studies where we would use animal models and interpret that data, and that can influence your calls. But it might be that the studies on the animals should be mainly limited to the exposures, and the gene clock and maybe the genetics would still be used, but be used in a different way. That's what I was trying to get at, but yeah. Right.
Yeah. In fact, because we were specifically told you were interested in human-related models, so to speak, I don't think we're there where we're going to start looking at humans from a genetic point of view. If you're carrying this clock allele, you're more or less likely to be affected by jet lag in that. So I deliberately did not get much into the genetic models, but you'll notice how yesterday I snuck a few of them in to make that point that I think, and let me just give you one example. The clock mutant animal, so a deletion, a mutation of the clock gene, gains more weight on a high-fat diet. The tau mutant animal, which is a different gene that's part of the core molecular machinery, does not gain weight on a high-fat diet. So, and then if we manipulate phase shift the light-dark cycle, we see similar differences between them too. So now I've got a way to go in and get at the mechanisms for how the environmental intervention is affecting metabolism in this particular case. So I really think the genetic models, and I would even go a little bit further, which you may not want to go there, but I've been converted, so to speak, that the fly really is an important model, the Drosophila. So I wouldn't even throw out the fruit fly as something that we, because the similarities that we're seeing in flies and in mice and in humans is just, I think that's kind of blown us away. The same genes are involved, and if we sleep deprive the fly, we see similar effects in the mouse and so on. So I think that the genetic models get at the mechanisms.
I think when you're talking about light at night, and particularly light and genetic model, the contribution of genetic model to understand how blue light affects mood cannot be underestimated. Means there's a lot of evidence that blue light or short wavelength of light might affect circadian disruption, melatonin, etc. But until after melanopsin knockout mice were made, and all of these effects are measured, we did not connect the photoreceptor to the physiology. So this is a clear example of genetic model contributing to our knowledge about light. And with that, there are still a lot of light effect on physiology and circadian disruption that we still do not understand. For example, the dim light effect on metabolism. Is it going through melanopsin pathway or an indirect pathway? That for those kind of questions, we still need those genetic models. Those exist only in mice so far.
Thank you. Dr. Gorman?
So I agree with, I don't think anything should be excluded. I would place a high priority. Well, Randy, I was not reviewer two. I swear I was. I was not. But I think that a diurnal model, and there are diurnal models. Not a lot of research, but I think it's very, very, in terms of its relevance to humans, I think it's much greater than the nocturnal mouse. And in terms of models, I mean, one model to really look out for, I think, is the marmoset model, which was established a long time ago, but is now becoming a favorite model with potential for transgenic animals and all sorts of sophisticated manipulations. I think it's a terrific model that there's probably not a lot of recent work on with regard to this issue, but Arbocanthus being the other. And I know Randy's got them in the lab, and other people do. The problem with these models is that we just don't have the same depth of understanding of the methods and all of this as we do with some of the others. But in terms of relevance, the nocturnal mouse is sleeping much of the day with closed eyelids, and so the issue that Mariana mentioned about transmittance applies to its daytime exposure, and the relationship between light exposure and activity has been established that light with activity is different, that the effects can sort of cancel each other out in certain respects, and so that relationship is deranged in nocturnal versus diurnal models.
Well, thank you very much. We'll continue down our expert panel, and then we'll take questions from others. Thank you. Dr. Figueroa?
I actually agree. I don't think we should exclude anything. I personally am agnostic to what animal model we're using. I think you have to pick the one that it's right to try to answer the question you set out to answer. And at the expense of being redundant, I do say that the one thing we have to make sure is that we understand the differences in the phototransduction mechanisms, and we're able to sort of equate the stimulus so that we're talking, we're comparing apples to apples and oranges to oranges. So that's what I think it's extremely important to keep in mind, regardless of what kind of animal models we're using.
Thank you. Dr. Nelson?
I'm a comparative biologist, and so I think you sort of have to study this wide array of different model species and appreciate what kind of information you can get. I appreciate mice are not little people, although I have some more friends as mice. No. But to your point, Mariana, I think that those of us who work on mice understand that this is sort of a point of discovery about mechanisms, and then it has to be refined in humans. And so I would say the same thing's true of the knockout mice, that what happens here, if you have a hypothesis that drives the question, then using the clock knockout might be appropriate to look at what the environment's doing to it. And I would say that nocturnal species are fine, Michael, if what you want to do is exclude some things. So if you want to exclude effects on sleep, we have our animals sitting during the day in former Mickey beer bottles that have been painted black, and so there's a wide opening that can go in there, but they're not getting light during the day, frankly. And if you want to use a strain that has melatonin of mice, like the C3Hs versus the black sixes, then you can rule out the influence of melatonin on your output. So I think that no animal model ought to be off limits, just because it can answer different questions. But mindful that they are not little people, and that you're going to have to take the mouse data and apply it. And the NIH ought to think about, and I've seen this happen in my institution, where you have parallel human studies and rodent studies going on, so that each study is informing each other at the same time, rather than waiting 10 years to do it.
Thank you. Dr. Stevens?
My comments are in the form of a question about melatonin-free mice. Those that don't have detectable melatonin, I know that there's some controversy in this area. There were certain strains that were thought to not produce melatonin, but the methods weren't sensitive enough. And what about melatonin receptors? Is there a cycle in your mice with melatonin receptors? a circadian rhythm of them, even though you can't detect melatonin at night.
Thank you. Would you like to? Oh,
I don't know the answer to that. I mean, I'd have to look up Ruppert stuff on that issue. But on the C57 blacks, I don't think there's a cycle of melatonin rhythms. Fred, do you know?
So I don't think there's much controversy that C57 black and most of the mouse strains that are inbred strains that are used do not produce melatonin because they got a defect in either one or two of the enzymes which are involved in converting serotonin to melatonin. But having said that, there still is, I have a particular interest of the fact that that's melatonin that's produced by the pineal gland that goes into the gut. There are other ways of synthesizing melatonin. It's not clear to me if C57 black is not synthesizing melatonin in the gut through different mechanisms, and I think that's sort of a wide open area. With respect to the receptors, they do have the receptors. Whether they cycle or not, I think everybody just said, well, since the melatonin's not there, we're not going to look. So I don't think we know the answer to that question. I could be wrong, but I don't think so.
thank you. And we had a question back here. Please identify yourself.
Hi, Doris Block.
Please go to the microphone.
Doris Plotica, Circadian, and Harvard Medical and Duke Medical. Whatever models you use, whether it's rodent, zebrafish, many of the other models, one of the issues with knockouts is going to be that it's going to affect development. And also it's sometimes difficult to study epigenetic factors because you've changed development so much. So a key strategy is to have conditional, obviously, mutants. And it's one of the things that we did in many of our facilities where we've done conditional mutants where you have normal development, normal function, and then you can perturb the function once they're an adult or at different key stages that are critical. And that may give you better insights into the actual mechanism than just a complete knockout would.
Thank you. I think we'll go on to the next question, if that's, or do you want one more response? Please go to the microphone.
Martin Moreed from Circadian. Can I add one more pitch for diurnal models? Because in fact, going back some old work of ours, 1978, I hesitate to add, when I was a really young Turk, squirrel monkeys able to show internal desynchronization created by light exposure at night, able to show failure of thermoregulation in other body systems. In other words, they could not defend against a mild cold pulse, and able to reverse it by creating synchronization using a food Zeitgeber, a food time cube. It's still in LL. So now what you're able to do is actually tease out the exposure of light from the circadian desynchronization itself. So that type of study can systematically now tease it out. And if you're interested, you can look it up in Science 78.
Thank you. So we'll move on to the last question. What biomarkers could be used to assess interventions to reduce light-induced circadian disruption? Dr. Blask?
I think this is a real challenging question. And I think just in general in medicine, I think that's one of the big challenges. And in circadian biology, I think it's equally, maybe more challenging. And I don't know. I mean, for me, again, I'm a melatonin person. Guilty. We can, and it has been used to a limited extent in epidemiological studies. The problem, especially measuring 6-sulfathoxymelatonin in the urine in the first morning void to give you an idea of what the previous night's integrative level of melatonin production is. And people always assume, well, that's what that represents what melatonin was produced the previous night. Doesn't take into account anything about phase, doesn't give you really other important circadian information. It also doesn't take into account, and not a lot of papers acknowledge this, and it personally bothers me why it's at least not acknowledged, that a level that you measure in the urine also represents what may have been metabolized by the CYP1A2 enzyme in the liver. So, then it's the question, does the person that you're using this marker to assess circadian function have some comorbidity that might affect their liver metabolism and specifically metabolism of melatonin? So that becomes an issue, especially when you're looking at populations that may have an important circadian component to their disease, like breast cancer, for example, or other cancers, who are taking harsh chemotherapy that affects their liver metabolism. So it just conjures up all sorts of issues of what does a one point in time measurement mean ultimately. So that's I think that's problematic, and that's all I have to say about that.
Thank you. Dr. Gorman?
I don't have much to say. I think melatonin might be the best we have, or maybe looking at actigraphy and sleep regularity and sleep quality, something along those lines, but I don't have anything more.
Okay, thank you. Dr. Figueroa?
Well, I think it will really depend on what kind of studies you're doing. If you're doing lab studies, you can probably do a lot more and look at a more complete array of biomarkers, cortisol, melatonin, clock genes, and so on. But when you go out in the field and you're trying to do these studies, I think as much as we want to measure, and I completely agree with you, Dr. Blask, about the timing. I mean, just one time point may not tell you a lot, but it will be very hard to get sort of continuous time measurements in the field. So I think this is a challenge because it goes between, how do you collect those biomarkers and what do they mean? But I agree. I mean, the ones that are, if you're looking at circadian disruption, I think you should do more than, I agree, melatonin without any question, but you should do more than melatonin. I think there's other biomarkers like cortisol, activity, sleep-wake cycle, all these things should be measured. And the challenge is how do you implement that in the field?
Thank you. Dr. Nelson?
Sorry, thank you. I think the biomarkers are just what people said. I think it's going to be the glucocorticoids and the melatonin, the DOMO, if you have them in a lab, salivary, if you're doing field studies, body temperature, being able to take fibroblast from the cheek and looking at the clock gene expression might be a biomarker also, I think we could do. And building on something that Dr. Turek said yesterday, these new sensors might help us a lot too. I know we're working with folks at the Wright-Patt Air Force Base, and they're monitoring their drone pilots. So those drones are being flown from Dayton, Ohio, halfway across the world, and they have chips on them. They're measuring their on-time cortisol, adrenaline levels, body temperature, all kinds of metabolites. And so I don't think that technology is too far behind, as Fred mentioned yesterday, that we'd be able to generate quite a lot of data from that kind of body monitoring.
Thank you. Dr. Stevens?
Yeah, I agree with everything that's been said, and also this notion of there might be a biomarker of circadian disruption that is in a blood sample. A paper just appeared in PLOS One, May 18th, 2015. Wendy Rodenberg, senior author. It's in mice doing transcriptomics in liver under various shift paradigms for these mice, finding real differences, then determining that there's a serum marker for CD36 that tracks with those transcriptomic changes. Now, I don't know whether this is going to work out for humans or not, But that would be nice to have such a marker. And then I do, as I already mentioned in my little talk about promoter methylation, I'm very excited about that result. I want very much to know if it's replicable.
Thank you.
I would like to introduce a word that I haven't heard yet, so it'll be new. And I think we're in the era of the Model T, where we're talking about melatonin, cortisol, and as Randy alluded to, the new technologies that are coming out are going to enable us to look at hundreds of different markers. And the term I wanted to use was timestamp. So we've got a DARPA grant. Ravi Allada's the lead on it at Northwestern. What we're trying to do is to do what Linnaeus did with his flower garden. So because flowers flower at different times of the day, you can walk in at any time and look at the flowers and say it's 2 o'clock in the afternoon. So we're trying to create a timestamp imagine if I was monitoring, I could be monitoring gene expression in the white blood cells, but we'll take mice and sacrifice them over every hour for 24, 48 hours, whatever, and I'll look at 100 different metabolites, and then I'll see the rhythm of all these metabolites, and I can line them all up and create a timestamp. Then I can go in and just take a single point, and I'll be able to tell you, this is the circadian phase this animal is at. And we will get to that state in humans we're doing human studies as well as the mouse studies. And so I think you want to be on the cutting edge of both the technologies that are developing as well as, this is a technology, I suppose, but it's the software and the hardware. The software and the hardware are coming together to enable us to do things we've never been able to do before.
Actually, Fred just said what I was going to bring to the fore, but I also want to bring up that there are already mechanisms, or there are ways of putting to work what Fred just mentioned, as well as Richard on the early publications for markers. There are some companies, I won't mention them, but have kits for self-sampling blood samples. And using the Linnaeus concept, when perfected or can be tested, with single or 2 times a day blood samplings by individuals such as shift workers. We're actually using those right now to study the circadian rhythms of individuals with essential hypertension and also doing pharmacokinetic studies. And we hope to use them for toxicology studies. So there's ways of getting dried blood, and you can also separate the blood from the cells if you want to do some white blood cell genetic studies as well.
Yeah, so I'm curious about the standard biomarkers that are already in clinical practice. We hear a lot that circadian rhythm disruption affects endocrine system and immune system. So then the question is, can we actually look at cytokine level or growth hormone level and can come up with a signature mix just like your timestamp, but this will be a arrhythmia or circadian disruption induced change in cytokine or inflammatory markers, or say glucagon, insulin, etc. And that will be extremely useful because those kind of tests are already existing and people can go to LabCorp or Quest and get those tests. Whereas even for melatonin, we are not even at that stage where we can go to LabCorp.
I might have little panels. So what we're using is panels. You can actually go out and get, we like sit around and say, let's get this panel because it's got 10 different cytokines that we think are interesting. Let's get this panel because it's got 5 hormones. And then in the end, we count how much are those panels going to cost, and we get down to, how many are we going to look at from a cost point of view. So there are these panels available, and they're going to be, and then I think, I'm not sure if it was Randy or not, but it was you, Richard, I'm sorry. Being able to look at things in the blood that are connected to liver function or kidney function, I don't care if it's actually going on in the blood. I want to be able to look at markers in the blood that are telling me what's going on in the brain. Because I can't do dissection of the brain in humans. Yet.
Just like, can you hear me? Just like to add to what Sachin brought up, right, about immune factors and relationship to specific diseases. biomarkers don't necessarily need to be just something circulating. It can be an elicited response. So in our mouse models, and Randy does similar experiments, after circadian disruption or light at night in his case, elicited response of immune cells dramatically changes, but circulating basal cytokines may not. So biomarkers may include collecting live blood, stimulating it, and then looking at the response of the white blood cells. And I think that's going to end up being quite useful.
Okay, well, thank you all for a great discussion for the light at night portion. I think we'll take a short 15-minute break, and then we'll come back and start with shift work.